In this video, we discussed the net change theorem and real-world applications of definite integrals. Started making this video at a different location and it got very noisy in the environment. So I had to change to a new location. That's why everything is already written down. Just as a review, we've already discussed this integral from a to b of f of x. And we said if the function is non-negative, so if it's positive or possibly zero on the interval from a to b, what this integral represents is the area between that graph of the function, the x-axis, which is represented by y equals 0, and the two vertical lines, x equals a and x equals b. But if that function is positive part of the time and negative part of the time on the interval of interest, what we end up with is what I would call a net area. We still are interested in the area bounded by the function and the x-axis, but whenever that area is above the x-axis, we add it, and whenever the area is below the x-axis, we subtract it. So the integral from a to b for this particular function is this area plus this area minus this area. It's just a number, and that number is equal to this area minus or plus this area minus this area. When we're evaluating this function, we tend to use the first fundamental theorem of calculus, that's the integral from a to b of lowercase f of x. And the first thing we do is we compute an antiderivative. And we typically denote that antiderivative by capital F of x. So then we evaluate that capital F of x at x equals a and x equals b and subtract. And that is the value of the integral. And because capital F is an antiderivative of f, it is a function that we can take the derivative of and get f back. That's how you can always check your work. If you take the derivative of an antiderivative, you should get the original function back. Now, there are lots of geometric applications of integrals. We've talked about this area interpretation, but we could also talk about volume. In Calculus 2, we'll learn to find volumes of solids with known cross-sections, volumes of solids of revolution using the disk method and the washer method. We'll find lateral surface area, and we'll also find surface area of more general surfaces in Calculus 3. We'll learn to find the length of a curve. And then we have lots of physical applications, fluid force, work, moment, and center of mass. Most of this is done in Calculus 2, and there are a few applications in Calculus 3 as well. But there are lots and lots of applications of integrals. But this theorem is the net change theorem, and this is our first opportunity to interpret the integral in real-world applications. So rather than having our lowercase f of x here as our integrand, we're going to replace it with that capital F prime. So we're saying the integral from a to b of capital F prime of x, that's the definite integral of the rate of change f prime of a quantity f, is the net change in that quantity f. So you evaluate that quantity at x equals b, you evaluate that quantity at x equals a, and you subtract. You would say, how is that a real-world application? Well, you see lots of real-world applications where you'll evaluate this, but it will depend on what the nature of this function is. It depends on what f is. It depends on what x is. If we know what f and x are, then we can interpret this as the net change in that quantity, whatever that quantity happens to be. So this is very general, but there are lots of applications. Here's an example. From the textbook. We're asked to let r prime of t represent the rate of growth or growth rate of a dog. And that's measured in pounds per year. If we know that r prime of t represents the growth rate of a dog in pounds per year, we can infer what r of t has to be. So the next question that they ask us is, well, what does r of t represent? And I think it's easy to see that if this is the growth rate in pounds per year, I think r of t must be the dog's weight. When it is t years old. You say, okay, well then, What about this? What does the integral from 2 to 6 of r prime of t represent? That's relatively easy to infer using the fundamental theorem of calculus. So I've got the integral from 2 to 6 of r prime of t. And the first thing we do is compute the antiderivative. Well, the antiderivative of the derivative is the original function. And then you substitute in t equals 2, and you substitute in t equals 6 and subtract. So you get r at 6 minus r of 2. Now that is a change in the dog's weight, or the change in the dog's weight from when it was t equals 2 years old to t equals 6 years old. So this is the increase or decrease in the dog's weight. It's probably an increase. So we'll say it's a change in the dog's weight from the dog's 2nd year of life to the dog's 6th year of life. From when it's 2 to when it's 6. And you'd say, okay, well, what about other applications? Well, if C of X represents the cost to produce X, let's just say items, and revenue is or R of X is the revenue to produce, or when we produce and sell X items, and profit is revenue minus cost. The profit due to producing and selling X items. In those cases, in those business applications, C prime of X or dC dx, R prime of X, which can be denoted dr dx, and P prime of X, which is dP dx, represent marginal cost, revenue, and profit. That's what we call them. And so this is how much the cost changes as we increase the number of items sold. It's going to be some number of dollars per unit. All three of these are going to be some number of dollars per unit. And if we say that, let's say C prime of 20 equals, let's just say $3 per unit, what that's telling us is that the cost per unit, or the cost is increasing at a rate of $3 per unit as we go from producing 20 units to producing 21 units. Similarly, marginal revenue, R prime of 20, let's say that's 50 cents per unit. This is how much income is coming in, revenue is income. Is how much the revenue increases as we go from selling 20 items to selling 21 items. So that's a very low marginal revenue. We only increase our revenue by 50 cents per unit as we go from selling 20 items to selling 21 items. And marginal profit might be some value as well. So this is the change in profit due to the the change in profit as the number of units increases by 1 at X equals 20 units. And since profit is revenue minus cost, this is R prime of 20 minus C prime of 20. So we might have 50 cents minus $3 or negative $2.50 per unit. So if these numbers were actually facts for some particular business model, if our P prime is negative, we might think that that's a problem. This says, as we go from selling 20 units to selling 21 units, we're actually losing $2.50 per unit. So this is not good when R prime and C prime have a difference that's negative like that. But now that we have marginal cost, marginal revenue, and marginal profit, if we were to integrate any one of those, we can use the fundamental theorem of calculus. And we get a meaningful number. In each case, what's the antiderivative of the derivative? It's the original function. So if we integrate marginal cost, we get cost. Get a net change in cost as we go from selling A units to B units. Or if we integrate marginal revenue, we get the revenue. And so that's actually going to be a net change in revenue as we go from selling A units to selling B units. If we integrate marginal profit, we get a net change in profit as we go from selling A units to selling B units. And so all of those are applications. And we can do this anytime our integrand is some kind of rate of change. One of the most common applications involves displacement, velocity, and distance. So let's say we've got the velocity of some particle represented by v of t. And that will be in feet per second or meters per second or miles per hour, some units of distance per some units of time. And we're moving along a straight line. So this is one-dimensional motion. You can think of projectile motion where you throw a ball up into the air, or you just drop a ball, or you throw it down. Either one of those is fine. Or you can think of just walking back and forth on the x-axis, like walking back and forth along a straight path, a straight road. And then you might designate some position as position 0. And then you can say, okay, well, how many feet am I to the right or left of 0 at various times? So we're moving back and forth in one dimension, and that's our velocity. And then you might ask, okay, if that's v of t represents velocity, what does the antiderivative of v of t represent? Well, v of t is the derivative of position. If s of t represents a position, v of t is s prime of s of t. So when I take this antiderivative of the derivative, what I get is that position function plus some arbitrary constant. Now, this is not a very useful function. If I actually had a v of t here and I was able to compute that antiderivative and somebody said, okay, well, what is your position at time t equals 5 seconds or t equals 5 hours? I would say, well, it's s evaluated at 5. That's going to be some position plus or minus some constant number of units, feet, meters, whatever, in either direction. You're like, it doesn't really tell you your position then if it actually has this arbitrary constant in it. So you're saying, well, what can we do? Like, how can we figure out what that arbitrary constant has to be? Well, we need more information. In order to find the arbitrary constant, we need to know the position at a particular time. We need to know s at a particular value of t. So we might say s of t naught is equal to s naught. Usually that t naught is 0 because we know the position at time t equals 0, and that's given to us. With this information, we can find the value of c that causes this to be our position function. And then if somebody gives us a particular time, we can plug that time into the position function and we can actually find out where that person or particle or whatever it is located. So we know that that's true. And you might say, okay, well then what does the integral from a to b of v of t represent? Well, That's the integral from a to b of s prime of t. First, we take the antiderivative. We just need one of them. We'll call that s of t. Then we'll substitute t equals a and t equals b. So this is the position at time t equals b minus the position at time t equals a. This is called the displacement of the particle. From t equals a to t equals b. Now, this does not take into account the fact that you are probably moving back and forth on this axis. If you're not just always moving to the right or always moving to the left, but sometimes you move right and sometimes you move left, you move back and forth, this doesn't take into account that history. It just says, where were you at time t equals b? Where were you at time t equals a? Subtract those. That's your displacement on that time interval from t equals a to t equals b. If you want to know the distance that you traveled, you actually have to think about when you were traveling in what we would traditionally call the positive direction, if this is the s of t axis, where s of t is positive on this side. So this is s of t equals 1, 2, 3, 4, and so on. Or when you are traveling in the negative direction. Are you going to the right or are you going to the left? That direction matters. Now, v of t, that velocity as a function of time, is ds dt. And that's defined as the limit as delta t goes to 0 of s of t plus delta t minus s of t divided by delta t. So if we look at this, we can see that displacement in the numerator. So I'm starting at some time t, and then delta t we're going to assume is positive. So we're moving in the positive direction. If we are moving from left to right, so that displacement is positive, v of t is positive. This delta t we're always going to treat as positive. But if we're moving from left to right, v of t is positive. If we're moving from right to left, this number is greater than this number, so we get a v of t that's negative. And of course, this is because I'm assuming delta t is greater than 0. Like, technically, delta t could be positive or negative, but we don't tend to do that. We do tend to think about displacement from one time right now and to it some time in the future. So provided that delta t is always positive, the sign of v of t is the same as the sign of the displacement. So we'll write that down. When v is positive, displacement is positive. And when the velocity is negative, displacement is negative. So if moving to the right is the positive direction and moving to the left is the negative direction, we're moving to the right when v is positive and we're moving to the left when v is negative. Okay, so we've got this velocity, the integral of v of t as the integral from a to b of s prime of t, so the derivative of position. When we compute the antiderivative, we get a function and antiderivative of this. It's almost a position function, but it might be off by a constant. We don't know what that constant is. But when we substitute b and a, we're subtracting that constant anyway, so we're still able to get the displacement. You might say to yourself, but how can I get the total distance traveled? What if I started at this location and then I went to the right for a little bit and then I went to the left for a little bit for a long time and then I came back to the right, and you're moving back and forth. Like, this displacement doesn't take all of that movement back and forth into account. If you want distance traveled, you actually have to integrate the speed function. So speed is the absolute value of velocity when you're talking about one-dimensional motion. So this will give you the total distance traveled. From t equals a to t equals b. So how far did you travel on that time interval? It would be given by the value of this definite integral. Okay, so with all of that in mind, these are all applications of the net change theorem. You say, well, what does the theorem say? It says if our integrand is a rate of change, the value of the antiderivative is just the original function that you took the derivative of to get that integrand, evaluated at b and evaluated at a and subtract. So the definite integral of a rate of change f prime is the net change in f. And the interpretation is going to depend on the application. And if you're saying to yourself, well, how can I know what this should be? One of the things that I look for when problem statements is something like these units. If I see pounds per year, this tells me the units of the numerator and the units of the denominator of this. So that tells me if I have this dRdt, it means that my R is some number of pounds and that my T is some number of years. When I see this C prime, that's dc dx, I know that I'm talking about some change in the cost per unit. So that's going to be some number of dollars per unit. Marginal revenue and profit are the same, some number of dollars per unit, or some number of cents per unit, or whatever it is, whatever the denomination of the money is in that particular location. And then when you talk about velocity, acceleration, and so on, you want to remember that position is usually represented by S of t, or sometimes it's X of t if you're talking about horizontal motion, or Y of t if you're talking about vertical motion. The derivative of velocity, or the derivative of position, is velocity, and the second derivative of position is acceleration, or you can think of acceleration as the derivative of velocity. If you have any one of these, you can find the other two by, if you have the acceleration, you can anti-differentiate to get velocity and anti-differentiate again to get position, but you'll have these arbitrary constants in your answer unless you have additional information. Those pieces of additional information are typically called initial conditions. And when we're going backwards from some function or some equation involving a derivative to try to find the original function, that's called solving a differential equation. So if you have a differential equation subject to those initial conditions, we can find those arbitrary constants, and then we can find some meaningful functions for our position, our velocity, and our acceleration. Okay, so let's look at an example. This next example deals with one-dimensional motion. We've got some particle moving back and forth on a line. But even though it's a little bit contrived, it helps us to understand these concepts. So let's do that. We've got t squared minus 5t plus 4 for t greater than or equal to 0. We can factor that. T times t is t squared. And if I'm looking for two numbers that add to give me 4 that, multiply to give me 4 that add to -5, -4 and -1 will work. So v of t is t minus 4 times t minus 1. The reason I factored that was because I wanted to make it very easy to figure out where that velocity was 0. That velocity is 0 when t equals 1 or t equals 4, when either of those factors is 0. So we know that that's true. And then when t equals 0, we know our velocity is 4. And then because this is a parabola, and the coefficient of t squared is 1, which is positive, we know it's a parabola facing up, and it's going to look roughly like this. Because of symmetry, that vertex is going to be halfway in between 1 and 4 at that like 2.5 location. And so this is our function. Okay, so this is our velocity function. There are lots of questions that we could ask ourselves about this function. Most of those are in my Desmos document, or it's not really a document, it's kind of a website. I'll show you those on Desmos, and then we'll do some of our calculations by hand. We'll keep going back and forth between the graphing calculator and then our hand calculations, and we'll see that we get the same answers either way. Okay, so we know that v of t is representing velocity, and we're told in the problem statement that it represents velocity in feet per second of a particle moving along a straight line. So I'm going to draw on my paper just a horizontal line. and I'll call that the S of t axis. And so we're just moving back and forth on the S of t axis. Now the velocity function, or the function t squared minus 5t plus 4 looks like this. It's that parabola with that vertex at x equals 2.5. It looks, I'm not actually sure what that y value is. It looks like maybe y equals -2. I'm not 100% sure. But we've got this function. We're not interested in the whole thing though. We're only interested in that part where t is greater than or equal to 0. So we graph that. This is our function. And then we have a number of questions that we could ask about that function. I also plotted the point when t equals 0, v of 0 equals 4. So that means at t equals 0 seconds, our velocity is 4 feet per second. And that's because of the units that were mentioned in the problem statement. We've got 5 or 4 feet per second when we're starting. You might say, okay, well, what does this tell us so far? Just looking at this, what does it tell us? Well, it looks like on the interval from 0 to 1, our velocity is decreasing. Let's say the particle's velocity decreases from 4 feet per second to 0 feet per second during the first second. So you might say, what does that mean? Well, it means the particle is slowing down. Now, the entire time the velocity is positive, so it's heading in the positive direction. If you're thinking of moving from left to right as the positive direction, that particle is moving in the positive direction from t equals 0 to t equals 1 second. But it's slowing down as it approaches a particular location at t equals 1 second. So let's write that. Let's say the particle is moving in the positive direction. If we choose a traditional, let's say, x-axis as our line of motion, the particle is moving to the right when the velocity is positive. Okay, so we know that. Maybe I'll put that in a different cell. Now from v equals 1 second to v equals 2.5 seconds, the velocity starts at 0 and then it gets increasingly negative. So at t equals 1 second, our velocity is 0, but then at t equals 2.5 seconds, our velocity is -2.25 feet per second. What does that mean? That means your speed is 2.25 feet per second, but you're going in the opposite direction. So rather than moving from right to left, you're moving from left to right because our velocity is negative. Did I say that wrong? Rather than moving from left to right, you're moving from right to left because your velocity is negative. You're moving the other way, but you're speeding up. You're starting from a velocity of 0 and your speed is increasing until it gets to a maximum speed of 2.25. So let's say that from t equals 1 to t equals 2.25 seconds, the particle is speeding up in the negative direction. Let's say that is the particle's speed is increasing and the particle is moving from right to left. Now from 2.5 seconds, that's the bottom here, to 4 seconds, our speed is, or our velocity is still negative. So we're still moving backwards. We're still moving in the negative direction, but we're starting to slow down. So we're going from -2.25 to -2 to -1 feet per second to eventually to 0 feet per second. So we'll say that in the next cell. From t equals 2.25 seconds to t equals 4 seconds, the particle continues to move in the negative direction, again, from right to left, but it is slowing down. The velocity decrease, or let's say the speed decreases from 2.25 feet per second to 0 feet per second. Then you say, okay, well, what happens at t equals 4 seconds? Well, then instead of moving from right to left, you start moving from left to right again. You start moving back in the positive direction, and that velocity keeps increasing. Since the magnitude of the velocity is increasing, your speed is increasing. So we'll say from t equals 4 seconds. Well, let's just say after t equals 4 seconds, the particle moves from left to right, and its speed is increasing. Okay, now we were not asked to describe the particle's motion, but we just sort of did. So I'm going to change that problem statement. Let's say this is part A. This is kind of how I write quiz questions. Part A, describe the motion of the particle based on the velocity graph. And that's what we just did. Okay, now let's call this part B then. Call this B, call this one C. Now you guys know how I write quizzes. Okay, so it says evaluate the antiderivative of v of t. What does the antiderivative represent? Actually relatively simple to find it. We'll do that on paper. So we have the integral of t squared minus 5t plus 4. Since the variable is t rather than x, we're anti-differentiating with respect to t, so you'll have a dt rather than a dx. And then we just use our basic rules, use the power rule. So we add 1 to the exponent and divide by the new exponent, bring the negative 5 down, add 1 to the exponent and divide by the new exponent. And then the antiderivative of a constant is a constant times t, and then we're going to add a constant. Now this is the antiderivative of velocity. So this is position in feet at time t seconds. I'm going to say up to an arbitrary constant. So again, it's not a very good position function, is it? Because if you told me, well, where are you located at t equals 1 second? I would evaluate s at 1, and I'd get 1/3 minus 5/2 plus 4 plus c. And I guess we could get a common denominator, multiply that one by 2/2, multiply that one by 3/3, get a 6 in the denominator, multiply the 4 by 6/6. And we get 24 plus 2 is 26. 26 minus 15 is 11. So you'd have 11/6 plus c. And say, well, our particle is at 11/6, so 1 5/6 along the s-axis. So right there, almost at 2. And you said, plus some arbitrary constant. So you're like, plus some number that would take me over there or over there. You're like, it's not a very good position function because it's got this arbitrary constant in it. So you'd say, well, what can I do so that my position function is actually meaningful? Well, I need more information. So we'll say the antiderivative represents this position up to an arbitrary constant. If we want to find the actual position without the arbitrary constant, we need an initial condition. So we need more information. S of some particular value equals S naught. and that would be given to us, and that would be given to us. Let's look at the another example on Desmos. So we've got v of t, oops, equals t squared minus 5t plus 4. And we'll anti-differentiate to get position. We have 1/3 t cubed minus 5 times the antiderivative of t to the first. So add 1 to the exponent and then divide by the new exponent. And then the antiderivative of 4 is 4t, and we add a plus c. And we'll just say c equals 0 for right now, but we don't actually know what c is. And we will say, what does s of t, or what does the antiderivative represent? Antiderivative of v represents the position of the particle in feet at t seconds up to an arbitrary constant. Let's adjust this. I'm going to call this part C. I know we've already got a part C. I'm just changing the problem statement as we go. Part C. Given that let's say given that the particle is initially 2 feet from the origin, find the position function. If they're telling you that the particle is initially 2 feet from the origin, that word initially tells us that at time t equals 0, s is equal to 2. So that what they're giving us is s of 0 equals 2. That's what they're saying. So if I evaluate this at s equals 0, or sorry, at t equals 0, I get 1/3 of 0 cubed minus 5/2 of 0 squared plus 4 times 0 plus c. So that just get a bunch of zeros plus c. So s of 0 is just c, and that has to be 0. Or excuse me, that has to be 2, because we're told that at time t equals 0, the position is 2. So that means our c has to be 2. So you substitute t equals 0 here. Simplify and get just on this right-hand side of the equal sign that expression equals c. And then you set it equal to 2, and then you would typically solve for c if there was something other than a 0 that was being added to c. But now it's just telling us c equals 2. So if we know that the particle is initially at 2 feet from the origin, that implies that c is equal to 2. So I am going to add a slider for c, and then I'm just going to require it to be 2. So this purple function now, or this pinkish purple function, is our position without an arbitrary constant in it. Like technically, any of these functions has that derivative v, it has the correct velocity. But if I change my c value, what I'm actually changing is my initial position. I'm telling you that at time t equals 0, if c is equal to 3, I'm saying the position is 3. If at time t equals 0, the c is equal to negative, or if at time t equals 0, our position is -4. So we're 4 feet from some origin, and we'll say we're to the left of the origin rather than the right. Then c would be -4. So at least in this particular example, when this part of the function evaluated at t equals 0 is 0, the value of c tells us the position at time t equals 0. Okay, so now we've got our position function. I'm going to call this one general solution. And then this s I'm going to call the particular solution. And it's just the original s. Plus that c, where the c happens to be 2 in this case, because of the information that we were given. Okay, so I'm going to call this d now, and then call this e, and this f, and then the next one is g. So the next part says, evaluate the definite integral of v of t from 0 to 5. What does the value represent? Well, it's easy to do in Desmos. We just type int and the integral symbol pops up, and you go from 0 to 5. And substitute v of t here. We've already typed it in, so Desmos knows what it is. Actually, it didn't know what it was. Thought we did. There it is. V of t equals that. Why is it having trouble? Okay, to find v in more than one place. Yeah, I don't see it being defined in more than one place. I only see it being defined there. Okay, I don't know why it's having trouble with that. Never has had trouble with that before. We'll just copy and paste that. No problem. There's always a way to work around it. So there's my v of t. The integral from 0 to 5 of v of t is this negative 8.3 repeating. The exact answer is negative 5.6. Now we can use the fundamental theorem of calculus to evaluate that integral. We should still get the negative 5.6, which is negative 0.833 repeating. And then we'll think about what it represents. So let's do that on paper. So we were asked to evaluate this. Now our velocity is s prime of t. It's the rate of change of that position with respect to time. When we compute the antiderivative, we're going to get s of t. We evaluate at t equals 0. We evaluate at t equals 5 and subtract. And so what we get is the displacement of the particle. From t equals 0 to t equals 5. So how much has our actual position changed, change in position from t equals 0 to t equals 5? Well, if we want to evaluate that for a particular function, we can use the fundamental theorem. So our function v of t was t squared minus 5t plus 4. We're going to compute the antiderivative, which we've already done. We've got 1/3 t cubed minus 5/2 t squared plus 4t. We'll evaluate at 0 and evaluate at 5 and subtract. So we'll have 1/3 times 5 cubed minus 5/2 times 5 squared plus 4 times 5 minus this expression evaluated at t equals 0, which is just 0. So we end up with 5 cubed divided by 3 minus 5 cubed divided by 2 plus 20. And if we get a common denominator, I'll multiply this by 2 divided by 2. So we end up with a 6 in that denominator, and I'll multiply this one by 3 divided by 2. So I have a 6 in the denominator, and then with the 20, we'll multiply by 6 divided by 6. I have 3 times 5 cubed, or 2 times 5 cubed minus 3 times 5 cubed is negative 5 cubed. Just subtracting 2 minus 3 divided by 6 plus 120 divided by 6. That's negative 125 divided by 6 plus 120 divided by 6. So we get negative 5.6 or negative 0.83 repeating. And again, you're like, what does that number represent again? That's the displacement of the particle. So I don't know where the particle was at t equals 0 here. If we didn't have this information from before, we wouldn't actually know what this value is. But I do know that wherever my particle was at t equals 0, t equals 5 seconds later, it is negative 5/6 of a unit from wherever it was at t equals 0. So we moved from the right to the left by negative 5/6 of a unit. So negative at 0.5 or at 0.83 repeating feet. That was our change in position from t equals 0 to t equals 5. Now, when we were doing the sort of solution of the differential equation subject to the initial condition on line, we said that S of 0 was equal to 2 because we were told that initially our particle was at position 2. So S of t in this case was 1/3 t cubed minus 5/2 t squared plus 4t plus c. And we said if we evaluate that at 0, we get a bunch of expressions that are all equal to 0. Plus c. So this is all 0 plus c, which is c. And then we set that equal to 2. And so then our position is this. It doesn't have any c's in it. This is a particular solution. And now with this in mind, it tells us we can find the difference between, or we can look at S of 5 and S of 0 and sort of visualize what we're talking about. If this is the S axis, S of t axis, this is S equals 0. At time t equals 0, we were at S equals 2. And then at time t equals 5, we evaluate, we get 1/3 5 cubed minus 5/2 5 squared plus 4 times 5 plus 2. That's going to be this number, negative 5/6, and then we'll add 2 to that. So we'll have negative 5/6 plus 12/6, which is 7/6. Is that right? So our person is here at time t equals 0, and then at time t equals 5, our person is right here at position 7 divided by 6, or 1 1/6 from the origin. So what is your displacement? Well, as the displacement from time t equals 0 to t equals 5 seconds is a displacement of negative 5/6 of a foot, or negative 0.83 repeating feet. So our person didn't move a particular distance, but the change in position from time t equals 0 to t equals 5 seconds was negative 0.83 feet, which just means we moved 0.83 units to the right, or excuse me, from right to left, when we take this difference between the two positions. Now we are asked to use integration to find the total distance traveled by the particle. So we can, if we want to find distance traveled, we don't want to integrate velocity, we want to integrate speed. So we will take the integral from 0 to 5 in this case. Of the absolute value of v of t. Yeah. So we get that 49 divided by 6. So that means the total distance traveled by the particle was 8.17 feet from time t equals 0 to t equals 5. You might say, well, how does that relate to this function? Well, let's look at the speed function. Speed looks like that. I think it's relatively easy to see. This is our velocity, that orange graph, right? Now, whenever our velocity is positive, the speed is the same as the velocity. But whenever our velocity is negative, the speed is the opposite of that. So we multiply these values by -1 and we get these values. When you graph the speed, it's much easier to see when the particle's speed is increasing or when the particle's speed is decreasing, or in the particle, yeah, it's increasing or decreasing. So in the interval from 0 to 1, the particle is slowing down. on the integral or interval from t equals 1 to t equals 2.5, the particle's speed is increasing, but we're moving to the left rather than moving to the right. From t equals 2.5 or 2.25 to t equals 4, we're still moving to the left, but the particle's speed is decreasing. And then from 4 to infinity, the particle is moving to the right and with increasing speed. So we can see that if we graph that function, and the integral of the speed in this case is giving us that total distance. So if we wanted to, we could shade that region. And they want us to use X for some reason. It doesn't actually make any sense to use X, but that's what I was told earlier, that you have to use X's in the inequalities on Desmos, which is bizarre. And so we've got that area there. So that area actually represents the total distance traveled by the particle. And I think that that makes sense when you think about the rate of change of velocity, or the rate of change of position with respect to time is ds dt. We're taking that change in position with respect to time, and we're multiplying by a tiny time interval. So we're getting a change in position. Now, if we integrate without worrying about the sign, it's going to treat every time we moved from left to right as positive, and then every time we moved from right to left as negative. So when we integrate, we just get that displacement. But if we want the true distance traveled, we want to include that distance that we traveled from right to left as positive as well. So we have to integrate the speed rather than velocity. So this area under the curve is ds dt times dt, or excuse me, the absolute value of ds dt times dt. So that instantaneous change in position with respect to time, when we take its absolute value, that gives us a distance. And then we're adding that up from t equals 0 to t equals 5. So that's what that area represents. And this one is very similar. Except we want to use this function here. We have to use X because for some reason Desmos doesn't like V of t today. Let's see. So we've got that on that interval, and then I also want the area between the function on the other interval as well. So this is distance traveled in the positive direction from left to right, distance traveled in the negative direction from right to left, and then this is distance traveled in the positive direction from left to right. So we're moving, so we've got some distance here minus the distance that you went when you went backwards, and then plus the distance that you went when you increased again when you went forward. Okay, then we said graph the speed of the particle. We've already done that. That's the speed. And then it says describe the motion of the particle and find a way to graph the motion of the particle on desmos.com. Ooh, it's kind of fun. So we've already described this motion. We said all of this about the particle moving left and right and up and down. Now we might want to graph that position as a function of time. Let's do that in a new graph. So I think I'm going to let my my x-axis be the s of t axis. I do not want to graph the y-axis. I don't want to graph the grid. I think I do want the step sizes of a step size of 1 on the x-axis. So here's our s of t axis. And we want to plot S of t. S of t is 1/3 t cubed minus 5/2 t squared plus 4t plus 2 because our initial position was 2. Now we don't actually want to look at this graph. What we want to look at is the particle at various times. So we want to plot the point t, S of t. Actually not a line, it should be a point. I don't know why it's having problems with that. Oh, actually, no, we're gonna let the y value will be equal 0. S of 0, 0. Let's plot S of t, 0. Here it is. What are they doing? Can't use t as a parameter of this function because t is already defined. Okay. Here we go. So at time t equals 0, we're at this location, and we're only interested in the t values between 0 and, I don't know, 10, let's say. Well, if we just play this, shows that particle moving back and forth. Maybe we should slow it down a bit. Now, if we look at the original graph, not the velocity, but the position graph. That's our velocity, and here is our position. This actually tells us the position of the function at every value of t. So it looks like our position goes from whatever that y-intercept is, a value of 2. Particular to a maximum. That maximum occurs right here at t equals 1. And that actually makes sense because we should have a maximum. We should have a maximum value of our position when the velocity is 0. Because look what we're doing. We're moving in the forward direction, but we're slowing down. And then briefly, when at time t equals 1, we stop. And then we go in the backwards direction. So we're moving forward, then we stop for a moment, and then we start moving backwards, right? So we go from a position of 2 up to a position of, it looks like 3.83 repeating, and then we start going the other way. And then we say, okay, when t equals 4, we are back at a position of 0. But anyway, so we've got a maximum position, or a relative maximum of our position at t equals 1. So we could plot some ordered pairs. This is where we start. That's our initial position. And then at t equals 1, we're at a relative maximum. So we're at, our position is at 3.833 on the t-axis, or on the s of t axis. And then we start moving backwards, right? Then at t equals 4, we're going to be at a minimum position. So it's 4 seconds. We're at this negative 2/3 position on the s-axis. And then we start increasing again. So our position is going from 2 to 3.83, down to negative 0.67, and then it just goes from 1 to infinity. And we can kind of see that if we're thinking of that particle as moving up and down in a vertical axis like this, going from 2 up to 3.83, down to the negative 2/3, up to infinity. But then we have a tendency to think of this as going from left to right. So if we go from left to right, this is what we see. So we had that maximum of 4, then we went back to negative 0.6, and now it just went off to infinity. So if you prefer, you could look at it on a vertical axis instead. Just a choice. We could do that. Then if we want to do that, we'll get rid of the x-axis and graph the y-axis. We'll call this one S of t. It would look prettier if it was in color. Max of 4, min of negative 2/3, and then it goes on to infinity. Guess we could plot that on this one, this graph here. Let's graph it on the y-axis. Let's not label that anymore. I don't know why it's having a problem with S of t. Oh, I'll call it S particular. And I think I'm going to plot that in orange this time. We'll see, we can see that label on it as well if we want to. Now, if I get rid of the velocity graph, it's a little bit easier to see. Trying to find it. Oh, actually, no, maybe we should have the velocity. It's really bizarre. That's it. All right, so I think we've done a lot with that question. So let's go on to another example. This one's not as insightful, but it's another net change example. It used some data, shows you at least how to use the regression capabilities of the Desmos calculator. So it says an experimental vehicle is tested on a straight track. It starts from rest, and its velocity is 0 in meters per second. It's recorded every 10 seconds for 1 minute. Says first we create a table of values and plot the points. So I've got t equals 0, 10, 20, all the way up to 60. And then I've entered these values from the table in the book. So I plotted those. And then it asks us to use the regression capabilities of Desmos to find the coefficients of a cubic polynomial that best fits the data. So if you want a cubic polynomial and you want it to be in the variable t sub 1, and I'm using t sub 1 and v sub 1 because those are the versions of t and v I used in my table. That way I could save v and t for the definition of the function itself. I just type v sub 1 tilde, and then I type my at cubed plus bt squared plus ct plus d. It's going, Desmos is going to find the values of a, b, and c, and d, so that we've got a cubic polynomial that best fits these data points. We've got this point, this point, this point, this point, this point, and this point. It's a little bit distracting that the graph is already there. So you ask Desmos to find the a, b, c, and d so that a cubic polynomial fits this data. And that's what it gives you. It tells you what a, b, c, and d are. If you want to see those, you can just type a, b, c, and d, and then just hit enter, and it'll give you these approximations. If you want fractions, it'll give those too as well. So our function v of t is v of t equals at cubed plus bt squared plus ct plus d. And then the question, what did it say? It says finally. Oh, I think the question said, find the distance traveled by the vehicle during the test. So that was actually the problem statement. So we'll say then to do that, we compute the antiderivative, which gives us the position as a function of time up to a constant. And then we'll model the track by a number line and assume the vehicle is initially at the origin. So we'll assume s of t equals 0 and t equals 0. And then we can anticipate the correct answer in advance by having Desmos evaluate the definite integral for us. So if I want to find the distance traveled during the test, basically I want the integral from 0 to 60 of not v of t, but the absolute value of v of t. Now, since the function is positive on the interval from 0 to 60, it isn't really necessary to compute the absolute value because the absolute value of v of t happens to be v of t. But in general, if you're trying to find distance traveled, you should take the absolute value. So I would include the absolute value just to remind yourself that if you don't, what you're going to get is a displacement. If you want distance, you really have to take the absolute value of the function. Now, if this is my v of t and I want to compute the antiderivative of this function, well, I just take the antiderivative of at cubed plus bt squared plus ct plus d, where a, b, c, and d are treated as constants. So we use the power rule. We add 1 to the exponent and divide by the new exponent. 3 plus 1 is 4, so we got t to the 4th divided by 4 multiplied by 1/4, same thing. Then we bring the b down, and then for the antiderivative of t squared, we get t to the, or you add 1 to the exponent, so you get t cubed, and then you divide by the new exponent. Dividing by 3 is the same as multiplying by 1/3. Then you bring the c down, and then you've got a t to the first, so you add 1 to the exponent, get t squared, divide by the new exponent, so you have 1/2. And the antiderivative of d with respect to t is that d times t. That looks like a differential. It's not. It's just a constant times t. So this is your position function up to an arbitrary constant. And then your change in position is s evaluated at 60 minus s evaluated at 0. So the displacement is 2,472.8 units. This is weird. I'm getting a different value for this and for this. They should be the same value. It's bizarre. Yeah, I don't really know why it would be giving me a different value. I'm using the same function. It should give you the exact same value since both functions are positive on the interval. The displacement and the distance traveled are the same in this case because the function is positive. So I don't know why it would be off by a tenth, but it's off by a tenth now. Okay. Guess Desmos is a little buggy today. All right. So I think that's it for our net change theorem. We're just going to use the fundamental theorem of calculus to evaluate these integrals. But remember, if you are integrating velocity, what you're getting is an integral of the rate of change of position with respect to time. The integral of a rate of change of position with respect to time is the net change in position. If we integrated the acceleration with respect to time, well, acceleration is the second derivative of position and the first derivative of velocity. So the antiderivative of acceleration would be velocity, and then we'd evaluate it, B, evaluated A, and subtract. So what we would get is a net change in velocity. These integrals are always giving us a net change in some function, provided that we can interpret the integrand as the rate of change of some function to begin with. With that in mind, we can interpret these answers in many applications. One thing to keep in mind, though, again, is that if you have the velocity function and you're asked for the distance traveled rather than the displacement, if that function is sometimes negative and sometimes positive, be sure to take the absolute value so that the value of your integral is what it's supposed to be. If you don't take the absolute value and the function is sometimes negative over the interval, you'll get the displacement rather than the distance.